Math 2414, Sequences, Video 6, Theorems about Convergence. Originally, I was going to cover all the theorems about convergence from this section in this particular video until I realized that that video would go way too long. So I'll make multiple shorter videos focusing on specific theorems about convergence, some of which will have specific names. Let's start with this first theorem, supposing a sequence is defined by an equals some function of it. Then if the limit as x approaches infinity of f of x equals L, then the limit as x approaches, not x, n approaches infinity, an is also equal to L. And you might be thinking you just said the same thing twice, that if the limit equals L, then the limit equals L. But the difference between these two is very subtle. It has to do with the variables and the values that we can assume. Whenever you see x in a calculus problem, you assume that it represents any real number, including all possible decimals. So when you take this limit, this goes through all decimals. More specifically, through all real numbers. So your x is moving from left to right, it's getting larger and larger and hitting every single possible decimal value along its way. But when you see a lowercase n in a calculus problem, you can almost always assume that it's an integer or a whole number. So this limit goes through all natural numbers. So n equals 1, 2, 3, 4, 5, et cetera, et cetera, et cetera. And you might be thinking, well, what's the difference? Well, the difference is when we're analyzing a sequence for convergence, we're looking at it discretely. We're stopping at each whole number along the way. But this over here, the limits that we've done before were all done continuously, meaning that your variable is going through all the decimal values. All this is saying is, if your limit goes to a certain place when it goes through every single whole number, and decimal and fraction and everything in between, then it has to go to the same place when it just stops at the integers. Now, believe it or not, this doesn't work backwards. A warning, this does not work in reverse. And when I say it doesn't work in reverse, what I mean is if the sequence converges to something, that doesn't mean the original function from a continuous perspective converges as well, which we'll see. Now, just realize that I titled this Theorems about Converge, not Theorems about Convergence. All right, so let's go to the first example. Suppose an equals n minus 1 over 2n plus 13, which without being restricted by the word processor in Zoom, I would write as n minus 7 over 2n plus 13 is a vertical fraction. And we want to know if this converges or not. Well, we can analyze its convergence by looking at this function continuously. In other words, what if this function could assume any real number, well, except negative 13 halves, that would make the denominator 0, and we wanted to know what its limit is. Limit as x approaches infinity of this function. Now we could play a few games here. We could play L'Hopital's rule, since the top and bottom both go to infinity. That goes to infinity, that goes to infinity. So we could take L'Hopital's rule, which says take the derivative of both sides. And there are some other algebraic ways that we can find out what this limit is. But since I brought up L'Hopital's rule, let's just go ahead and use it. If you ever see me write L apostrophe H over an equal sign, it means that I'm using L'Hopital's rule to say that the limit I'm looking for is equal to the following limit. Take the derivative of both sides. The derivative of the top is 1, the derivative of the bottom is 2. This limit is now independent of x, so it's just 1/2. Therefore, sequence an approaches 1/2. So that wasn't too bad. But again, the difference between this guy up here, which I'm about to highlight in yellow, and this guy here is that the one on the top only uses whole numbers. or natural numbers, or positive integers, whatever you want to say. Whereas this one uses all real numbers. I guess instead of saying uses, we could talk about domain. But all the theorem says is if your function does something for every single number, then it's got to do the same thing for the integers out of that. But it doesn't work backwards. For example, let's take this sequence, an equals cosine of 2 pi n. If we were to just analyze this sequence by cranking out some values, you would discover really quickly that not only does it converge, but it converges to a particular something. Let's just start by putting in values at the end, starting with n equals 1. Put in 1, we'll get cosine of 2 pi. Put in 2, we get cosine of 4 pi. Put in 3, we get cosine of 6 pi. Put in 4, we get cosine of 8 pi, et cetera, et cetera. But your trig skills should be good enough to know that all of these have easy answers. Not only do they have easy answers, they're all the same. Break out a unit circle, radius is 1. Then 2 pi means that you would start from 0 radians. 2 pi is a complete revolution, so you would end up back here. And the cosine would be the x coordinate there, which is 1. So the sequence starts with 1. But then for cosine of 4 pi, you would just make another revolution, end up at the same place, and have the same x coordinate. Every one of these is equal to 1. So it should be pretty transparent that this sequence not only converges to 1, but it gets there instantly from the beginning and never leaves. So it's a constant sequence. It's always equal to 1. But limit as x approaches infinity, cosine of 2 pi x does not exist. Even though the subsequence you form by stopping at each integer creates a convergence sequence that's actually constant, as a continuous function that can take in every possible value of x, this limit does not exist. And the reason is real simple. I know what the graph of y equals cosine of 2 pi x looks like. We'll get back to that in a minute. I know what the graph of f of x equals cosine of 2 pi x looks like. I'm not going to reach each trig here, but number one, we all know the graph of cosine does this. You should know that on the y-axis, when x equals 0, it starts high. And the thing you may have forgotten, which hopefully you didn't, is that the period of cosine is 2 pi, but when you have a coefficient in front of the x, you divide the period by that to get the new period. So if the original period was 2 pi and the coefficient is 2 pi, divide those and you get a period of 1. This graph starts at 1 on the x-axis, makes a complete cycle before it hits 1 again. And when it hits 2, it'll do it again. So this is clearly a cosine graph or a sine curve, if you will. And it never settles down. As we move left to right, it's always oscillating up and down like this. So the sequence converges, and it converges to 1, but the function that generates it from a continuous perspective fails to converge, diverges, you could say, by oscillation. It doesn't blow up, it just keeps doing this. So you got to be careful that when you see a theorem like this, it says, if this thing happens, then something else follows. You can't always say it in reverse. In other words, we can't say that if the sequence converges, then the limit that generates it, then the function that generates it has a limit that goes to the same place from a continuous perspective. All right, there is one more theorem about convergence that I'd like to go over, but there's a setup. This theorem says, let's say that we have two sequences that we already know converge. Some sequence an that converges to some limit L, and another sequence bn that converges to some limit m. Then we can say a lot of things. In fact, I'm going to say 6 things, but you'll probably be able to figure out what they are pretty quickly. If we define a new sequence by adding terms to sequences, then this will converge, this converges to L plus M. In other words, if you add the terms of two convergent sequences, then the new sequence converges sum of the limits of the original two sequences. And of course, we can say the same thing for subtraction. This converges to L minus M. If you form a new sequence by multiplying terms for two given sequences, then that sequence converges product of their limits. And of course, if you form a ratio of sequences, or the ratio of terms of two sequences, that converges to L over M if M is not equal to 0. Another good surprise there. So basically it's saying that if you combine two convergent sequences, you get another convergent sequence. And the limit of the new sequence is however you combine the original sequence, you do that, original sequences, you do that to their limits. But there's two more that belong on here. I'm going to see if I can put them in the space down here. If C is a real number, you know what? If C is an element of the real numbers. If you're not familiar with the symbol for is an element of, there it is. If you're not familiar with the symbol for all real numbers, it's called a double script R. Things like that if you draw it better. But it basically says for any real number, any C an element of the real numbers, for any number that's a real number. Then you form a sequence by taking an original sequence and multiplying every term by some constant that converges to L. But there's one more, and I can't fit it on this screen. If you're wondering why I don't use it at the top, that's where I put my picture. But you know what? Let me move my toolbar over and we're going to put it up there. So what I'm about to write up here, just pretend it's down on the bottom below everything. If E is greater than 0, positive number, then can't see, but the screen's jumping around. I'm grabbing the bar at the top accidentally. If P is greater than 0, then the sequence, the nth term raised to the P power is equal L to the P. And we could probably even say greater than or equal to 0. But putting the 0 there would be silly. Anything to the 0 power is 1 except 0. And that's the reason we exclude it, because one of the terms might be 0. 0 and 0 would be undefined. All right, so this basically says that convergent sequences behave. You got two sequences that go to two places. You add them together. The place they go to is the sum of their destinations. Same if you subtract, multiply, or divide. If you multiply by a constant across the entire sequence, then it converges to that same constant times the original limit. And this works for powers also. All right, I want to warn you though that it doesn't go backwards. For example, if we take the first part that says if two sequences converge, then their sum converges, that doesn't work backwards. So this is a warning. This doesn't work backwards either, because the first theorem didn't work backwards. There are theorems that work forwards and backwards. They're called biconditionals, but this one doesn't work backwards either. Here's a real easy example. If I can draw, for example, if we take, oh, I don't know, 1/2 10th power plus, I don't even need to get this fancy. Let's say we have, well, let's just say 2 to the nth minus 2 to the nth. This clearly converges to 0, because each term is equal to 0. But if I view it as two separate sequences that I took the difference of, both diverge to infinity, to be honest with you. So the difference of those two sequences converges to 0, but individually neither one converges. So you can't take apart convergent sequences into multiple convergent sequences, but you can combine convergent sequences into a new convergent sequence. So that's all I was saying when I said it doesn't work backwards. All right, so in the next video, we'll look at some more specific types of convergence theorems that have some special names.